Hello and welcome back. I'm sure you would have enjoyed that refresher time. Time to have some a drink or bit stretching your arms and legs and get that energy back. Now let's see what this session is going to unfold. I'm going to show how the stack works in the program. So let's go into the program. I already downloaded the IDE. I'll just minimize this for explanation. So I'll minimize this, minimize all of this. I'll open STM Cube IDE to explain how the stack works. It's loading on the background. Once it's loaded, I'll show you. As you already learned how to download the STM32 Cube IDE from the links from session 4, and also you know how to create a project, and also you learn how to write your first program to blink the LED and to control that LED via a switch. So I'm sure by now you would be more familiar how the IDE operates and how it works. So I'm sure this session will help you to understand a bit faster because you went through the basic setup and basic things already, and now you would know how things move on. So it's loading on the background. Once it's loaded, I'll show you and I'll start with the example. Still it's loading. Just give me a few moments, please. Because when you start STM32 Cube ID at any time, when you completely shut down, when you restart it, it has to do a lot of internal checks. Like it has to go through file checks before anything. So it has to relate and integrate and link everything, and that's when it will be ready to start from the previous sessions or wherever you left. So I think it's ready now. One sec. Okay, it's ready now and it's happy, so it's downloaded. Okay, I'm going to create I'll close all of this, or I'll leave it there or close it up to you. I'll start with fresh. I'll close, I'll delete all of this so you won't get confused. I'll start from scratch. Delete this, don't need this. Okay, and delete that, delete. Sometimes if you ask too many operations to do, you get the ding tone, and also you get that messages to avoid, to just give you a notification to say, are you really want to delete? If so, yes. Okay, then delete. Okay, so now it's all clear. So you have to go to file, new, and we're going to create a STM32 project because we are learning for the target, and this will start to initialize and ask you to select the target. The target will be the Nucleo board STM32F411RE. It's loading. It will be loaded shortly, and then we can march in. Okay, still loading. So this is what it's doing. It's selecting all the files and it's linking with the server files before it allows us to connect to that target board. So just bear with me, it's happening at the background. Once it's ready, then we would be able to move for the next step. As you can see down here, it's talking to its internal applications, and it will come back when the ID is ready. So it's in progress to set the target board. So patience is a bit key here. Sometimes the ID does a lot of background checks before to make everything easier and set up easy for us. Yay, there it is. So the first step, as you know, is you need to set the target selector. As you know, it's a nuclear board F411. You can click on the drop down and you can go all the way to select that nuclear board F411RE. If not, you can type in there and this name will come, and you select there, and then you click this to start and click on next, and you're going to give a name today. So today we are learning about stack, so I will name it as stack, and I'll start with project type as empty and then finish. So as you know, the source file generally comes with 3 different source files. .mainc, the if you remember, it will come as the startup files, and it will have its linker description files. So as you can see, it's already generated that for us. Okay, so the source, it has system call and system memory, and the startup will have these 2 files, the flash and the RAM. So double click on main C. As I said earlier, these are all for reference for your writing, to let others know that what you are programming for. So your file name, who has written this project, and where this sits. Is it in main program body? And a bit of an attention note, it's copyright. Like sometimes third-party people may want to use the program in bigger industry, so that's why they need to put a copyright message, so they don't get pirated in the end. So that's that. Let's get into the interesting bit. So I'm going to show you from scratch, so I'll delete all the unnecessary files, and then let's start. So I'll include the standard input output header as well, and then let's go into main. I'm going to just create a small function first. Yeah, I'll start with a small function. So again, is it small function int. I'm going to call func add, and then declare the arguments int a, int b, int c, and int d. These are all the arguments. So you have to prototype and define the function. Then you need to write that function and tell what that function is supposed to do. So I'll just copy that. So we're writing the function. Always start with open braces and close set braces, so you won't get any form of error. So I'm going to declare a variable to store the result. So every function returns with a value, so that's where your result will be stored in sum. What would sum do? Sum has to do the addition. Sorry. Plus d and return sum. So that's the first function that we just added. So your function is ready, and you're going to call that into your main function. So call that you declaring a local variable, and then you're calling that function here into that local variable func comma add, and then the arguments that you're going to add. So I'll show you step by step. So I'm just adding whatever inside the function is, and int c, int d, and then as you know, the main function has to return your result, and every function has to return with the result, so therefore return 0, and that halts that. Okay, now let's see, go there and build the project to see if it is error free. So right click on the project name and then start to build. This will check with all the registers and check with your line by line code and come up with any errors, if it shows or any errors. Okay, it's showing us 4 errors. Warning, variable sum set but not used. Set variable. Okay, it's taking as the arguments, and it's saying that function is not used in anywhere, so it's okay. So now we need to give just a value, change that into some locations 1, 2, 3 and 4, and now save and build the project again. This will clear as we set the values to it. Okay, 0 errors, that's what we are after, and it's lovely that it comes as 0 errors. And let's proceed to the next step. What is the next step? Because STM32F411 comes with a built-in debug operation, so we can set your debug values. So to rectify and analyze your program, you have to set to as debug function. So for that, right click on the program, the project name, go down to debug as, and start your debug configurations. So once the debug configuration window opens, then you have to double click the STM32C C++ operation, and by default whatever project you are working on, your application will be linked to that. So see, stack debug and the project name will be representing the same, and by building the project it will generate the stack.elf, the ELF executable linker format file, and make sure your application points to that, otherwise it will show a lot of error in debug perspective. So that's that, it links to your ELF, and then you go to debugger tab. 2 things as you would remember from earlier sessions. In the interface you have to enable the ST-link for for the processor, for the IDE to know that you working on the target board, and also the output view where you're going to view. So you need to enable the serial wire viewer. So these 2 are the must, and then click apply and then debug. So this will start to move from your perspective of what to say, your C application to debug perspective. So that's what it's saying. So just give me a sec, it's still analyzing the background. I'll do another debug as and changes debug configuration and debug. Yeah, and then click on debug. Okay, this could be a couple of things. It's saying there is no ST-link detected because we chose the ST-link, and that's because I unplugged the USB cable and I left it with the target board unplugged, so I'm reconnecting back to initialize that step. Yeah, that's the happy noise, the little ding ding ding, which is really good. So now we can build again and start to set the debug. Just to make sure it's going to the hardware. So that's why I ask you to get the hardware, so you can also get all of this and you will start to learn. So as soon as you hit that hardware connection, the warning would disappear, sorry, and then you can go to see the debug option. So go to debug option. Because I already set the configuration, so you don't have to reset it again, but just to double check, go to debugger, see that ST-Link is enabled and the serial wire viewer is enabled. If it does, then click on debug, and this will change the perspective from your C to debug options, where you would be able to see all the registers, the stack pointers, and all of that in the format of registers. So it's processing. As you can see, it's 70% done. Once it hits 100%, then it'll ask you to, or prompt you to switch from C to debug mode. Waiting for debugger connection. Yes, yeah, switch to debugger mode and wait for it. It's still on 90%. Okay, so this is the one we are after, and here we are. And if we go to registers, by default your breakpoint in the program will go and stop on the function execution point, where that's where you're linking your result to the function. So this is where the execution point stops, and this is what you would see in the registers. So if you go to registers, open the registers. So these are the general registers. Click on the down arrow to get the registers. So these are all the stack pointers from R0 to R12, and the R13 is your current stack pointer. So if you put your mouse in there or hover your mouse, and what you read, that's your current instruction pointer. So your stack pointer will show the current stack pointer location where it is. And the first four, R0, R1, R2, R3, R4, has the argument values. So whatever you given inside this argument, int A, int B, int C, int D, so these are all the values. These all showed in not in hex format. So to see in hex value, right click there and go to number format, change to hex. So you would be able to understand. Or generally go to value, number format, change to hex, and that will change. Hex changes. So initially the value of the R and R1, R2, R3, the arguments, the value is 2000 and 000. So that's the SRAM. Remember from the slide, the SRAM has the start address and the end address. So this is the start address 2000 and 00. So likewise, if you change this value to hex, you will see for that, and for this, that's the hex value of R. So if you scroll down, further down, what by default your program runs on the thread mode, and by default the thread mode, the stack pointer will always have the main stack pointer. Whatever value you have in the main stack pointer will have the same in your stack pointer. So 0 cross 2001 and triple F zeros, that's what in the MSP, and that's what's showing in the stack pointer. And by this time the processor will ignore the PSP, doesn't know and doesn't want to do anything with PSP, but you can change and allocate this PSP to the stack pointer by initializing either before main program or inside the main program. You have to reinitialize. So you can do in two ways, either before the main program or after the main program you have to reinitialize. To do that, you need to include and show it in the format of assembly language, so it would be much easier for the compiler to understand and give the proper push of the stack. So I'm going to show you a small code about how to write a small assembly language. You don't have to go deep into the assembly language. This is just for our understanding, to learn how the stack works. So I'm going to show you how the assembly language, and you can see for yourself how the stack pointer can be changed from MSP to the PSP location. So bear with me one moment, and I'm going to write a small snippet of codes. So just wait there. Okay. As I said earlier, the MSP, the main stack pointer, where you get this MSP pointer, if you go to the startup file, the startup.x, double click that. So the MSP address starts from here. You get the value R0, R1, R2, R3, and the addresses for that value would be down. Also, it can be in the linker description file, so you can click on the linker description, and that's where your linker description is. And initially it will start with the E stack, so that will have your origin of RAM and its length of the RAM. So you have the initial built-in 128 kilobyte of the RAM, and its starting address. As I said, the RAM will have starting address and the end address. So this is the starting address, 2004040. So this is the starting address, 2000000. And there is a separate section for understanding about the linker scripts and the startup file, so don't worry much about it now, just to understand it's there. And these are the values. It's taken from those two files. So and it has that internal magic in the compiler, so everything is linked. So that's why they are there for a reason. So I'm just pointing it out where they are and how you get that into the program that I'm going to show you, how you have to include that assembly language to move or load from MSP to PSP, main stack pointer to processor stack pointer. Okay. In order to do that, I will create first to show the data location. So I'm going to create a variable to show how this stack operation here it changes and how that's going to change. So I'm going to use the terminate and relaunch option, and you will see for yourself how. Okay. Just one moment. Debug configuration. Yes, debug. Yes, go to debug. It's going to change and show you the debug value in there. Go to debug perspective. It's on 70%, so once it hits to 100, then we will be in the debug. Yeah, switch. And we need to see what happens to the data 10, how and where it sits in the stack pointer. So you got to go to registers, you need to click on that, and then you need to go step by steps to see the step instruction, how it changes. So I'll go to step into first. It's checking with the main, and see the main is adding the data 10 to it at the program counter. Step into, so now it returns to the main function of sum, so you won't see that data 10. So all the code 0 1 2 3 4 0 1 2 3 4 is assigned, and the data 10 it reads from where that is the FFD0. So now the data 10 is added D0. So step in, you go to return and then do another step in, add 32 and another step in, and return values. So this is how the FF0, the initial stack pointer, now changed to, before it showed as D0, so that means the value accepted and the new value came in and it's all added, it's like embedded into the, it gets pushed in. But how to change the MSP now, because we are still in the thread mode, there is no interrupt or exception handled to the function call, so it doesn't matter whatever it's in PSP, so the program doesn't care. So I'm going to show you how you can change that into your program by writing a small assembly program which you have to use. So inside main, you can give this as change SP to PSP. So this is reinitialization after, you can do it either before function or after main function, and you can write it inside the main function. And also you need to tell where you're going to generate. So you're going to generate an exception handler as well. Generate underscore exception. So I included two functions so that I can show you how to change the stack pointer from MSP to PSP and what happens when you introduce an interrupt or an exception. So what happens to the stack pointer. So those two been included, and now you need to write a small assembly language program to make it understand. So don't worry much about the assembly language program. And then you're going to call that function void change from stack pointer to process stack pointer. Yeah, process stack pointer of void, and then you need to give the attribute. So you got to start from writing the MSR location by assembly language ASM. You have to say what state it is a volatile, and you need to give MSR, and you're going to give the first argument value the process stack pointer value. So this is where you're going to understand and let the processor know that you're going to use the stack memory. I'll simply copy this, and then now you have to set the SP select bit to say you're going to use PSP. So MSP will be changed to move R0 to a control location. So MOV R0. It's not RO, it's R0, sorry, R0. And then location 0 cross 0 to where it has to do. It's similar. I'm going to set select bit. Again, we are telling and calling the select bit, so calling that and give its value MSR to control. Please don't worry, I'm just making you understand with the assembly language. It is called inline assembly language, where you can also use inside the C program, but you have to include an attribute. Attribute is the assembly language program, where with that the C program will understand there is an assembly language. So this is what you have to do. Okay, and then you're going to retain that value in the result. So to return, you need to link, you need to use a linker to return. So now that's done. This is to return the value. So I have written a simple assembly language to introduce the change of MSP to PSP. So now I need to include the starting address, because the startup, the SRAM has to know where it's starting from. So I'm going to include the starting address of the SRAM, which is which you can get this in the data sheet. EKU SRAM end. Come on, the stack pointer starts at SRAM end, so 0, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, and you have to add that to the location of your internal SRAM memory. So 128 times your bits of 1, 0, 2, 4. Okay, so that's, leave it at that, 1024 and the bracket. Okay, so that's the address, and also you need to give the PSP start address. So initially the 512 will live there, and then now you need to separate MSP to PSP. So you need to allocate another 512 bytes to represent where your PSP location going to live. It lives after SRAM. So EQ PSP start PSP underscore start at the end location, and then you're allocating another 512 bytes to it. Allocating 512 bytes to it. Okay, so that's the SRAM end. You have given the location start address and then where the PSP actually starts, so you describe that, and now loads from the SP LDR are not PSP start. So then the next step, you need to paste that volatile, and you need to tell the LDR for not where the process starts from PSR start. Okay, so that the LDR now will know to write the program SP select 1. So the PSP code, that's done. So now we need to write another function for the exception. So copy this, and I'll write another program. Copy generate exception of Control C, come out here, Control V, start that as another function of void generate exception of void, and start the function. I'm going to set the location for the generate exception where it is, so we'll copy one of these. Again, please don't get too much worried about writing this, because we are learning about embedded C, we are not learning assembly language. So please bear with me. I just want to write this to show how the stack pointer moves from MSP to PSP. So just please bear with me. You will learn that shortly. Sorry, I have written this earlier before I wanted to explain. So I'm referring back to my notes and writing it so I don't make any mistakes. So that's why it's taking a while. So just please bear with me. The location I want to show is on 02 because that's where you listed there, 02. Okay, that's there. This goes to startup file and take the exception handler. So you need to get the exception handler from the startup file. So click that yes. If we go here, the exception handler will live in here. Stack reset handler, and you got the SVC handler. So you need to copy that, copy, and go to your main program, and you have to include that into your main program. After it returns, then call that void control V SVC handler void, and write another function. Okay, here you're going to see the result. So print you're going to say in SVC handler SVC handler is, and then show next line character, and then finish your program. Okay, now we included the exception, the interrupt, and also we asked to change from MSP to PSP, and we return a small assembly code to do that. So now it's all ready. I'll go and complete the project, and I will check for errors now. So I'll go and build this project. Bad instruction BX LR expected E found in there. Generate exception return of 0, generate SRAM 1 2 3 4. Okay, what did I miss? Generate. SP select equal to 0, expected comma after SRAM, expected comma, generate exception return 0. So I open this bracket, close the bracket, open the bracket, closed bracket, closed, closed. I'll recompile again. LDR error in bad arguments. It's saying 113 is the LDR. Okay, BX control, just bear with me. I did some mistake with my function calling. Just not printf. Printf to say print. So this should rectify a problem. The 6 errors in BX error, bad instruction. Bad instruction error. printf in SPC handler. Okay, you got to some volatile LDR0 or not SPSP. Yes. Okay, LDR PSP, so there should be LDR0 where it starts. LDR0, there shouldn't be. Build again. Okay, just bear with me. I will rectify this and I'll show you how this MSP and PSP work. I'll be back with you shortly. Just don't go anywhere. I'll work this on the background, and once it's ready I'll explain.